Imagine we have a ramp. It has some slope. At the top of the ramp, there's a wall with a spring connected to it. That spring has a stiffness K. Now, we attach a box to the ramp, to the spring. That box has mass M, and it stretches the string some amount. X naught. And the box falls into an equilibrium position with the spring. Then say we take that system again with the box, and we're going to pull that box down by some other amount. Let's say we pull it down an amount, xm. So first we put the box on there, and it went down a little bit. Then we pull it down xm, and we release it. So that box flies this way because it's pulled on by the spring, and it's set into a simple harmonic motion with the spring. And we want to find two things. Where does the box rest at its equilibrium position? And what is the period of that oscillation? After we pull it down and release it. We'll start with this first question. So at this equilibrium position, we have our ramp. At this position, the box is not moving, so it has zero acceleration, which means the net force on the box is zero. So there's two forces on this box being pulled up by that spring, and it's being pulled directly down by gravity. So we can draw a free body diagram. We have that force from the spring, and we have that force from gravity. Oh, and it also has a normal force, since it's in contact with the ramp. Now, the spring can only move along the ramp. So we're gonna establish some axes. We'll say up the ramp, in the positive direction, down the ramp, in the negative direction. Now this force of gravity has a component down the ramp. We'll call that Fg parallel, and a component into the ramp. We'll call that Fg perpendicular. And Fn and Fg are equal to each other, so they cancel out, which means the two forces that we care about on this box are spring force going up the ramp and this Fg parallel down the ramp. At equilibrium, the net force on the box, which is net force equals Fs plus FG parallel. That has to equal 0. So if we look at these magnitudes, we have net force equals Fs, which is positive because it's up the ramp, minus Fg parallel equals 0, or Fs equals Fg parallel when the box is in its equilibrium position. We can use Hooke's law, which says that spring force is equal to negative Kx, where K is the stiffness of that spring, and X is the displacement, how much the string is compressed or stretched by. And it's negative because if we pull the box down, so we have a negative X, then that force, that spring is going to pull back up, which gives a force in the positive direction. So we have negative Kx equals Fg parallel, which, if we look at our free body diagram, theta is right here, and that's the same theta here. And this component is this side of the triangle. So we can use trig to get Fg parallel is equal to Fg sine theta, or negative Kx equals mg sine theta. And we can solve that for x. And actually, this is x naught since we're looking for the position that the box rests in. So we have x naught equal to mg sine theta divided by negative k. Although we're just interested in magnitude of x naught. So we have x naught equals mg sine theta over k. Then the box rests at a position along the ramp, which is x naught below here. So x naught equals the sine theta divided by k. Now, we could use this angle, and maybe if we knew the length of this ramp, we could find out how far up here the box rests if we wanted to. Now, once we pull it down and release it right here, that box is going to start oscillating. And if we graph that motion, let's graph it. We're going to graph that box's position along this ramp. Maybe it's in meters versus time, which could be in seconds. So we pull it down an amount, xm, and that's negative because down the ramp is negative. And we're going to say this position right here is x equals 0. Simplify it a bit. So that box, once we release it, is going to start oscillating like this. So it's going to be a sine wave or a cosine wave. And it turns out the amplitude of that oscillation is the amount that we pulled it down by. It never goes farther away from that equilibrium position than that. So this is x equals 0. This also has a period, which is the time it takes to make one full oscillation. So it starts down here, goes up, then it comes back down. That's one full oscillation. Or one full oscillation could start here, then it goes around, comes back here. And that is the time that we want to find. And that's going to be time, maybe in seconds. Now we could write an equation for this. So x is a function of time. It has an amplitude, xm, and we're going to say it's a cosine wave since it starts at its amplitude. It's also going to be negative since it starts down here. Since a normal cosine wave would look this. Cosine. And then it has some angular frequency, and it's a function of time. This is somewhat the general form of a sine or cosine wave. So generally we might write x of t equal the amplitude. Maybe we have a sine wave. We have an angular frequency. And we might have some phase shift. Although we're just going to say ours is 0, since this just determines where we put t equals 0. And then it could also be shifted up some amount, maybe t. And our c is also 0 since we put our equilibrium position at x equals 0. That's just a general equation. In this box, while it oscillates, also has some velocity. We can graph that. That might be meters per second versus time in seconds. So it starts down here with 0 velocity. Then it starts going up. And velocity is the rate of change of position, or the slope of this graph. So it's 0, then it starts going up, positive. Then right here, it reaches a maximum slope and it starts going back to 0. Then right here, it's back at 0 again. Then it starts going down. And right here, it's still going down, but it's trending back to 0. And right here, it's back to 0 velocity. And then that just repeats. So that was one full oscillation. This point lines up here. And our velocity has the same period as our position. So this period is the same as that period. And we can write an equation for this. Let's say the maximum velocity it reaches is Vm, Vmax. So we have an amplitude, Vmax. This is a sine wave since it starts at 0 and it's positive. Starts going up. So Vmax sine. It has the same angular frequency and it's a function of time. Now we have a function for position and a function for velocity. And we also have some acceleration. This box accelerates meters per second squared, and that's going to be versus time. So acceleration It's the rate of change of velocity. So we start at some positive acceleration. We're going to trend with decreasing velocity towards zero acceleration right here. That's zero acceleration. Now we have negative acceleration, increasing in the negative direction to here. Then right here it starts going back to zero until there it has zero acceleration. So right here, zero acceleration. Then it goes back to positive acceleration, maximum positive acceleration there. Then it goes back to zero acceleration here. And then that trend repeats as well. Zero acceleration, zero acceleration. That's this one. Over a little bit. Then we have a maximum acceleration. Call that A max. And we can write a function for acceleration. A of t is A max for our amplitude. That's a cosine graph. And it's positive because it starts up here. Cosine. And it has the same angular frequency. Now we have three functions for position, velocity, and acceleration. We can relate those in the way that drew them. So we said v of t is the rate of change of x of t, or v of t equals d t of t equals the time derivative of xm cosine omega t. Now, the derivative of this is, we can use the chain rule since we have omega t in this cosine function. The derivative of omega t is omega times the derivative of xm cosine is xm sine, or negative xm sine. So we have negative omega xm sine omega. And that looks something like this. We have negative, oops, this cosine was negative, and negative. So the negative of negative becomes positive. Now this looks just like this function. We have an amplitude times sine of omega t, which means Vm actually is equal to omega times our position amplitude. Now we can do the same thing for acceleration. Acceleration is the time derivative of velocity. So acceleration equals the first derivative of Vm sine omega t. So k of t equals derivative of omega t, omega times Vm cosine omega t. But up here we found Vm was equal to omega times xm. So we have k of t equals omega times xm, or omega squared times xm cosine of omega t. And that looks just like this function. And we have our amplitude. So A of m equal to omega squared times our position amplitude, or our maximum acceleration, equal to our angular frequency squared times our maximum displacement. So if we can find our maximum acceleration, and we also know our maximum position, then we can calculate our frequency. Or if we could find our maximum velocity, then we could also use that to calculate our angular frequency. We're going to start with this one. So notice, we look back at our graphs, our maximum acceleration occurs at the same time that our maximum position occurs. Maximum acceleration corresponds to maximum displacement from our equilibrium point. So if we can find the acceleration after we've pulled our spring back here, we can find our angular frequency. Before we do that with our ramp spring, we'll simplify it a bit. Let's say we have a new spring. It's just a spring on a horizontal table, a horizontal frictionless table. That box has mass m, that shows spring with stiffness k, and this table does not have any friction, totally smooth. So there's some forces acting on here. We have gravity, normal. These two forces cancel out, and the only force, the horizontal direction along the movement of the box, is the spring force. So if we draw a free body diagram, the only force that we care about is gonna be that spring force. Because these other two forces cancel out. Now, when we attach this spring, this box, to this spring, the equilibrium position doesn't change at all. So this x naught for our horizontal spring is just 0, because there's no force of gravity or anything that pulls it down. And then when we pull it back and release it, we have some initial stretch. Say we pull it back. That amount, xm. Then our net force on the box is, this is our net force. Its spring force is equal to k times xm. Then we have acceleration. We take Newton's second law. We can rearrange that and get A equals net force divided by mass. So our acceleration of this horizontal oscillating box, right when we release it from this initial stretch, is A equals A xm over m. And because this is the initial stretch we found up here, that initial stretch corresponds to our maximum acceleration, or that maximum stretch or displacement corresponds to maximum acceleration, which means this is our maximum acceleration. We can also show that by seeing that this acceleration is proportional to our stretch. So of course it will be the greatest when our stretch is the greatest. Then we also have am equals omega squared times xm. So if we come over here, omega squared xm. We can then relate these two expressions. So a m over m, that's our acceleration from Newton's second law, equals omega squared xm, that's our maximum acceleration from taking the second derivative of our position function. And we can solve this for our angular frequency. So xm multiplies both sides, xm. So we can cross that out. And then we get omega by square rooting both sides. Omega angular frequency equals our spring stiffness divided by the mass of this box. How can we get our period, though, from this? This is only our angular frequency, which is different from our real frequency. So angular frequency is how many radians the box might buy. If you imagine this is in radians. Every second. And our real frequency is in revolutions per second, or oscillations per second. And one full revolution or oscillation is equal to 2 pi radians. That comes from the idea of this being on a circle. If you imagine our position is the horizontal axis through this circle, the vertical axis might be time, or the vertical axis could be anything. Then once we move from here, we make one full oscillation, return here. That's 2 pi radians. So to get from 2 pi or radians per second to how many things of 2 pi radians per second, we'll divide omega by 2 pi. We could also take an example. Say our angular frequency. Let's imagine angular frequency is 10 pi radians per every 1 second. We divide that by 2 pi. We get a real frequency of 5 revolutions per second. So frequency equals omega over 2 pi, or omega equals 2 pi f. Now we can take these two equations, come up here, and we get 2 pi f equals square root k over m, or frequency equals 1 over pi square root k over m. And then period, the relationship between period and frequency is frequency equals 1 over period, or period equals 1 over frequency. So period and equals pi. 1 over this is 2 pi square root m over a. We got this result by taking a horizontal spring, like this one, saying our net force is equal to the spring force, kx, giving a net force that's proportional to our displacement. But what about for our slanted spring? Well, we'll look at that. Let's examine a few scenarios. First, we have the equilibrium position with the box. We have two forces. We have spring force going up, Fg parallel going down. So our net force equals Fs minus Fg parallel equals 0. Or K x naught, that's x naught right here, minus Fg parallel equals 0. Now this position corresponds to this spring when it's not stretched or compressed any. Now imagine, now let's say we do stretch this a little bit. So here, I'll annotate that first stretch. So now, we've pulled this out. So now, it had that first stretch from attaching the box. Then we stretch it some more before releasing it. Let's call that delta x. So our net force comes from the same Fg parallel going up. But now Fs is greater because our total stretch is bigger. So our net force equals Fs minus Fg parallel equals k x naught plus delta x minus Fg parallel, or k x naught plus k delta x minus Fg parallel. And we'll notice that we have these two terms, kx naught minus Fg parallel, and we know from over here, those two added together equals 0. So we can cancel that out. And we find our net force equal to k times the amount that we pulled it down by. Now what if Now how about when it's on the way up? So first we pulled it back, or first the box sent it down a little bit, but now it's on the way back up, and it winds up here a little bit. The spring is still compressed, this little amount. So we still have the same force, gravity. Now we have a smaller spring force still going up. So our net force still Fs minus Fg parallel, which is K. Now we have X naught minus delta X. Give this stretch minus Fg parallel, or K X naught minus delta X, or K delta X minus Fg parallel. We see we again get these two terms, and those cancel out, leaving us with a net force to negative K delta X, pointing down because now the box wants to return that equilibrium's position. And we find that between both of these scenarios, that net force is still directly proportional to the stretch from our equilibrium position, which is this delta X we're now dealing with. Let's look at one more scenario. Now, spring has come up so much. Maybe it started over here. That was X naught. Now, our delta X has brought it all the way up here, past the initial spring's position, and now the spring is being compressed. So now we have Fg. That's still constant. Now the spring is actually compressed some amount. So we have a force, a spring force, pushing it down. And our net force is then negative Fs, since it's in the downward direction, minus Fg parallel. Or K X naught minus, oops, this is delta X, minus delta X. Now this term will actually be negative since delta X is larger than X naught. So we move this negative to here, minus Fg parallel. So we got K X naught minus K delta X minus Fg parallel, which still leaves us with these two terms, which cancel out, and our net force equal to negative K delta X. So we find that even though our spring is on a horizontal slope, so that in addition to this spring force, we also have gravity pulling it down, the net force on the spring, on the mass, while it's oscillating, is still directly proportional to its displacement from its equilibrium. And all this slope did was move that equilibrium from right here down by an amount x naught to here. So it's not on a slope. The equilibrium stays here. We slope it a little bit. The equilibrium moves. And we could even put it on a vertical spring. And the equilibrium would just move even more. And then the rest stays completely the same. So delta net force still equal to a delta x. So then we can use A max equal to k delta x over m. Then we get omega equals square root k over m. And we get the same result over here of period equal 2 pi times square root m over k. So we have our period equals 2 pi square root m over k. We also found that we have a relationship between our maximum velocity and our angular frequency. So if we can find our maximum velocity and we know our maximum displacement, we can calculate our angular frequency. So we'll come over here and look at our horizontal spring to simplify it a bit again. So we still just have this one horizontal force, which means our net force is going to be the spring force, which is k times whatever our displacement from equilibrium is. And now we're going to look at the energy stored in this spring. So when it's over here, when it's at, right when we pull it back, first we pull it back a little bit. Let's say this position right here is equilibrium. We pulled it back an amount, x. That gives it potential energy, since we had to exert a force on it over some distance to put the box and spring into this configuration. Now we release it. That potential energy is converted to kinetic energy. So right here, all of our energy is potential energy. That's going to be spring potential energy. Then as that box flies this way, it reaches this equilibrium position and it's moving over here. Now the spring isn't stretched any, so there is no potential energy. No force would be required to put this box into this position, just as it is. And all of this potential energy converted into kinetic energy. So we have a lot of kinetic energy. And then it oscillates back and forth. It comes over here. Now it has potential energy again as it turns around. And that process repeats. So if we can find the potential energy that we put into the system by pulling it back, then we can compare it to the kinetic energy at this point, hopefully find the velocity at this point. So spring potential energy is given by US spring potential energy equals 1/2 k x squared, and that's the spring constant times the displacement squared. And this equation comes from the definition of potential energy. So potential energy is the work required to move an object from some initial configuration, So let's say that's our equilibrium position to wherever we put it. In our case, that's our maximum displacement. And that work equal to the integral of our force over that displacement. And since force is kx, that gives us potential energy is equal to 1/2 kx squared from 0 to xm. So we can compare that potential energy, US, at this point to our kinetic energy at this point, which gives us an expression, 1/2 k times our maximum displacement, xm, squared, is equal to 1/2 m v squared, which is the equation for kinetic energy. 1/2 multiplies both sides, so we can cancel it out. And solving for v, we'll divide both sides by m, so we get kx squared over m, then v equals square kx squared over m. Now we can pull out that x squared to get v equals x, and that's xm. xm square root k over m, and v is also equal to, how we found up here, omega xm. Now we have xm multiplying both sides, and we get omega equals square root k over m. Now we can do the same thing we did last time. We get omega is equal to 2 pi f, then f equals 1 over 2 pi square root k over m, and t equals pi square root m over k. We got that result by looking at the energy conservation during this oscillation of our horizontal spring. And for our slanted spring, our energy conservation looks a little bit different. So right here at equilibrium, we might say we have 0 gravitational potential energy, but we do have some spring potential energy. And then here we lose some gravitational potential energy and we gain some spring potential energy. So that would be a little bit more complicated to solve it like we did here. But importantly, we still see that that net force on the spring is still directly proportional to delta x, and it's equal to k delta x. So we can still get the total potential energy using this function, and we still get the same result because the force that is required to move our box from its equilibrium position in the slanted example is still equal to k times delta x, which still gives us a total potential energy equal to 1/2 k x squared, which still gives us the same result of v equals xm square root k over m, and then period is equal to 2 pi square root m over k. Turns out that for any object, that force is directly proportional to displacement from an equilibrium So if we can write the net force to that displacement times some constant for a spring that is stretch or compression times this, that will yield this same expression for potential energy, where potential energy is proportional to the displacement squared. That results in this oscillatory simple harmonic motion.